So we're going to finish up with dot product today. And I want to emphasize that whenever a question asks about the angle between two vectors, what we want to do is think about the dot product, because that's our formula that has the angle in it. Now we made two formula for the dot product. The first one, A dot B, was first component times first component plus second component times second component plus third times third. So if we have the vectors in component form, we can calculate the dot product. And of course, I've written this down for a three-dimensional vector. This works for any dimensional vector, assuming, of course, that A and B are of the same dimensions. You can't dot product two vectors that aren't the same dimension. We also made this other sort of a geometric dot product formula, magnitude of A, magnitude of B, cos of the angle between them. We can, since they're both dot product, we can use this relationship that these two pieces are equal to solve for the angle. Now I know in the book they write out a theta equals arc cosine of, but I think it's easier to just have us remember the two versions of this dot product formula and then solve for the theta each time. So whenever we're talking about the angle between two vectors, think dot product. Also, whenever we're thinking about the angle between, and we're going to get there in a couple of videos, the plane and a vector. So if I'm talking about a plane and a vector, and I want to know what the angle between the plane and the vector is, we still think about dot product. So because the plane is defined by its normal vector, and I have a normal vector for the plane and another vector that I'm talking about. If I want the angle, I'll get, so let's say normal vector perpendicular to the plane. This other vector, if I want the angle between the vector and the plane, I can get the angle between the vector and the normal vector to the plane, and it's just 90 degrees minus that. So anyway, whenever we talk about angle between vectors, dot product. So let's get our angle here. I've got two 3D vectors. We want to find the angle between these vectors. So let's figure out what the dot product is. So I need, and it doesn't, we already showed that it doesn't matter what order I dot product these in. So I'm just keeping them in the order that's presented, but it doesn't matter. So the dot product of those vectors is going to be first times first, 1 times minus 1, plus second times second, plus third times third. And when we clean that up, we get minus root 6. Because we got a negative answer, we know that these vectors must point in kind of the opposite directions. So the angle I expect, or I will solve for, the angle is going to be bigger than 90 degrees. So there's our dot product. We also need to get, I need to get the magnitude of the two vectors. So let's take the magnitude of this first vector, which is going to equal to the square root of the first component squared plus the second component squared plus the third component squared. So that's square root of 8. Likewise, I need the magnitude of the second vector. Square root of first component squared plus second component squared plus third component squared. This ends up being, and you should figure that out, you should check that on your own, root 3. So now let's plug into this side of the equation. Magnitude of A, and again, it doesn't matter which one I think is A and which one I think is B, but we just did this in order A and B. So I'm going to have magnitude of A times magnitude of B times cosine of the angle between them is equal to A dot B, and that's our minus root 6. Oh, my bad. I copied the wrong thing here. This magnitude, magnitude can't be negative. That's our dot product. That looks better. Magnitude of A, magnitude of B, cos of the angle between them equals the dot product. And now we can solve this for cosine theta. This is going to be root 24, which, okay. When I cancel that, that's root 4, so I get minus a half. I knew it was going to be negative. So the cosine of theta is equal to minus a half. That means that theta, that's a special triangle, minus a half. Theta must equal to, got to think about arc cosine of minus a half, 60 degrees. We can write 60 degrees, or let's keep it in radians. Pi over 3. Oh no, not 60 degrees, because it's got to be minus 2 pi over 3. So the cosine of 2 pi over 3 is minus 1/2. So now I've got the angle between the two vectors. A more common thing to do then is a question like, show that these two vectors are orthogonal. Orthogonal means perpendicular. Orthogonal means they intersect at a right angle. It's 90 degrees between the vectors. So basically I need to show that the dot product is 0. That'll show me that the vectors are orthogonal. So I need first vector, dot product the second vector. All right. First times first, 1 times minus 1 is minus 1. Second times second is another minus 1, plus third times third. That does equal 0. The vectors are orthogonal. They're perpendicular. Prove the Cauchy-Schwarz inequality. So we've got our Cauchy-Schwarz inequality, that the dot product of two vectors is less than or equal to the product of their magnitudes. This looks like we can prove this. This almost looks like our A dot B formula right here. So let's take this formula that we've already proven and use that for our proof. This is a true statement. Now, now the proof kind of makes sense, because the cosine, the biggest the cosine could ever be is 1. So we're always taking magnitude of A, magnitude of B, multiplying it by a fraction, maybe 1, maybe even negative, and having it equal. So we're always making this side, we're making the AB smaller. Let's think about this in a proof type structure. I know that cosine theta is always less than or equal to 1. That's true. Now I'm taking both sides of this inequality and I'm multiplying both sides of this inequality by magnitude of A, magnitude of B. So this is true. I'm taking both sides of this inequality and multiplying it by this positive number. Because I'm multiplying by a positive number, I don't have to think about flipping the inequality. And now, get rid of this. Well, this is equal to this magnitude of A, magnitude of B cosine. That's equal to, so I can put this up here. That's equal to A dot B. And so A dot B is less than or equal to the product of the magnitude. We've proven the Cauchy-Schwarz inequality. And we've proven it in n dimensions. Our proof from other previous videos, sometimes we've had to say, okay, let's just do this in 3 dimensions and prove it in 3 dimensions, and then you can see how the proof kind of extrapolates up to n dimensions. Here we didn't have to specify a dimension, so our proof is good in Rn. Let's do another proof since we're on a roll here. I want to prove this triangular inequality, this triangle inequality. Before we do that, let's just think about what the triangle inequality means and why it is the triangle, why it's called the triangle inequality. Gonna grab some pencils, pens, need some vectors, got to make a triangle. If I call this vector A and this vector B, if I add them together, this vector on the end here that connects them would be vector A plus B. Makes a triangle. A, B, A plus B. The triangle inequality says the length of this vector has to be smaller than the sums of the length of the red vector and the other pencil vector. Why does that make sense? Well, this couldn't be bigger because I'm going to grab a bigger, I need a bigger vector than this. I need something longer than the A plus B. So I'm going to grab, I'll be back. Okay, I was just going around my office trying to find a longer stick. I have this for lab work. So this vector is way longer than the sum of these two vectors. And I can't make a triangle because these two vectors won't reach. Duh, you can't make a triangle with 3 sticks and one of them is longer than the sum of the other two. That's all the triangle inequality is showing. I mean, it makes sense when I wave sticks around, but let's prove it in algebra. Why do we have to prove it in algebra? Why can't this just be enough of a proof? Well, all the stuff that I'm holding to show my vectors as a proof, it's more of a demonstration, all the stuff I'm holding is in 3 dimensions. Our proof is going to be good for 4 dimension, 5 dimension. We can prove this in Rn using algebra. Let me put this back and think about our proof. And I'm going to use then to prove this inequality. I want to use this idea that the magnitude of vector A plus B squared is equal to the magnitude or the dot product of that 2 vectors and expand that out. We got that from all the way up here when we talked about A dot A is equal to the magnitude of A squared. So a vector dot product itself is its magnitude squared. A vector dot product itself, the vector in this case is A plus B, is equal to the magnitude squared. So let's expand that out then. That's going to be, and I'm using the dot product, that's going to be A dot A plus 2 A dot B for the inner and outer. I get B dot A and A dot B, but we know they're the same thing. Plus B dot B when I expand this out. So I'm trying to show, let's focus on what we're doing. I'm trying to prove this triangle inequality. Because both sides are positive here, if I could show that the square, if I squared both sides, that this was true. If I could show this was true, then you would square root both sides and say the original triangle inequality is true. So I'm trying to get to here. That's what I have on this side. So I'm trying to show this is true. If I could show this is true, then this would be true, then this would be true. The triangle inequality is true. Magnitude of A, or sorry, A dot B, this is magnitude of A squared. So let's clean this up a bit. I'm going to end up showing my proof upside down, but it's more clear as to where it comes from. So A dot A is just magnitude of A squared. B dot B is magnitude of B squared. And let's expand out this side here. These are just magnitudes. So that's going to be equal to A magnitude of A squared plus 2. This isn't dot product. This would be magnitude of A, magnitude of B. So here's me squaring out this side. So to show what I want to show, which is the top line, I have to show this second line, expand it out as the third line. If I could show this is true, then I could go back up the chain and finish my proof. Well, looking here, oh, Cauchy-Schwarz inequality is going to help me out here. Cauchy-Schwarz inequality says that the dot product is always smaller than the magnitude. So let's go back up to let's start our proof with that Cauchy-Schwarz inequality. So I'm starting my proof. All of this was thinking. Let's start our proof with the Cauchy-Schwarz inequality. That's true. So if that's true, then if I multiply both sides by 2, that's still true. If I add A squared and B squared to both sides, it's still an inequality. So I'm adding that to one side, I'm adding that to one side. Still an inequality because I added the same positive amount. Same idea here. You guys see where I'm going with this now. I'm adding that to both sides. That's true. Oh, and now I know that this is equal to that, and I know that this side is equal to this. So now I have my proof. This equal less than. So square root both sides. Cauchy-Schwarz inequality is proved. No, my bad. That we use the Cauchy-Schwarz inequality. The triangle inequality is proved. But more importantly, it's proved for any dimensional vector. So my stick argument works in 3D. If we drew it on a piece of paper, we would have our proof in 2D. But now we've got our proof in n-dimensional space. The triangle inequality holds in n-dimensional space for vectors.